In this lecture, we shall learn how we can design PEB structures, that is pre-engineered building structures. Now, those who are not comfortable with the steel structures or who does not have any experience, PEB might sound somewhat difficult to you. That is, what exactly is PEB and why it is called a PEB and how it is different from a conventional steel structure. So basically, it is called pre-engineered building structure because we basically do the overall engineering of the structure. Like in conventional structure, we can take some ready-made sizes of structural steel columns or something like that, but in pre-engineered building structures, we design the structures as per the bending moment diagram, as per the bending moment flows in the structure, and as per the shear force diagrams of the structure. Now, because I want to explain everything to you in a detailed manner, so this lecture series might be somewhat long, but I hope at the end of this lecture series you shall be comfortable with PEB structures and your visualization shall be good. So first of all, to start with this lecture series, I want you to Google PEB XAML PDF, because basically there are in Dubai or in Middle East or in Asian continent, Kirby and XAML are the two main PEB vendors that do supply the most of the pre-engineered building structures. So they are the most reputed people to design the pre-engineered buildings. So there are various PDFs or various literature that is available free of cost on the internet regarding the pre-engineered building structures. So if you will Google the PEB XAML PDF, there will this open this second file here, that is XAML Steel Technical Manual. So they had given various literature regarding all this pre-engineered building structures, but I want you to open this one more file here, that is this docshare02, this slideshare.net. So there is this one document on the slideshare.net, the steel structure design manual for engineers. Open this file, and here you can see this steel structure design manual for engineers. You can download from this link. So they had also explained regarding all the materials that can be used and all the standard codes and how to plan PEB structures and how we can design the mainframes. Jack beams I shall also explain in the lecture series, how to design rigid frame connections, etc. And before I explain you everything about this technical concept, I want to have your visualization good also regarding the PEB structures. So you can Google the Kirby PDF, and there's this technical handbook by Kirby Building Systems. So if you will download this Kirby PDF and Kirby Technical Manual, so this is somewhat more detailed manner as compared to the XAML Technical Manual. So this is basically the PEB skeleton structures. So like in the warehouses or in the various you must have seen some various Walmart buildings or various Amazon buildings or Amazon warehouses. So most of the warehouses are usually built like this in the PEB structures. So this is basically the skeleton of PEB, and so this is basically the footing at the bottom. So all the pre-engineered buildings must have some foundation. So this is the concrete footing here. After that, number 2 is the anchor bolt. So anchor bolt serves as a connection between the steel columns on the top and the RCC footing at the bottom, and it makes sure that all the forces that has been generated at the top of this pre-engineered building structure are effectively transmitted to the foundations and the pedestals. And number 3 is the base plate. So base plate is basically the interface between the steel columns and RCC pedestals. 4th is the end wall gut. So there are these two terms that you should know. Number 1 is the purlin, and number 2 are the guts. So here you can see on the number 19, these are the roof purlins. So this is the roof purlin and these are the wall guts. So that is why at the number 4 they had highlighted these wall girts. So on these, the purpose of these wall girts is to hold the sheeting. That is, we cannot left the structure open. So on the top of this whole PEB skeleton structure, we shall install either the sheeting or we shall install either the wall panels. And after that, number 5th is the portal bracing. So these are the portal bracings that has been made here, and this is the thing that this is called the portal bracing. Basically, there are two types of bracings in the PEB structure. One is the wall bracing, and second is the portal bracing. So this is called a wall bracing. That is, we brace the structure either by wires or by rods, and these are basically the tension structure. That is, only tension is allowed in these bracings. Whereas this portal bracing, the purpose of this portal bracing is that we brace these two portals with the help of another portal. I repeat this line. This is called one portal, right from this point to this point. This is called another portal from this point to this point. And we can brace these portals with the help of this another portal that has been made here. And the purpose of this portal is to brace these two portals. Now, you must be thinking, if we are bracing this structure with the help of this wall bracing, why we need to assign this portal bracing? Sometimes it too happens that maybe at this phase, because all of these bracings have been made here, so it might happen that the designer may need the bracing here also. But there might be a case when there must be an entry from this phase. So to make an entry to this phase, designer usually provide this portal bracing. After that, 6th number is the main frame straight column. 7th number is the wall bracing, that they are either used in angles or rods or cables. 8th is the framed opening. So this is called a framed opening because these are also made with the help of girts, and the purpose of these framed opening is to make space either for the window or for the louvers. Louvers are basically made for the ventilation purposes. So if you don't know louvre, you can Google it, and after seeing the picture, I'm sure that you will understand what exactly is a louvre. 9th is the end wall wind column. So these are the end wall wind columns. So basically, these are the portal frames, and this is also called a gable end frame. So at the end frame, we make sure that if we want to make a sheeting, we do need these wind columns also. So the purpose of these wind columns is to make sure that we can make these wall girts also, and to effectively make a perimeter around the whole structure also. So this wall wind column is a must or an essential for a PEB structure also. 10th is the roof bracing, and number 11th is the main frame rafter. So this is called a main frame rafter. Number 12th is the jack beam. So jack beam is also a very interesting concept that most of the people also don't know. So this is basically called a jack beam from this point to this point. Now you must be thinking why we are making this jack beam here. I want you to notice the columns arrangement here. So a column rises here, it goes all the way to the top here, and then it goes all the way to the bottom, and then it goes bottom right here. Similarly for this portal, similarly for this portal, and all the way to the end. But what exactly happens here? Here you will see that the portal starts here and it goes all the way to the top here, but it on the way from this point to this point, there are no columns in between. So this span must be very long, and the bending moment must be considerable for this type of arrangement. So to break this span from this point to this point, or to provide support to this portal, we do provide this jack beam. So the purpose of jack beam is to basically break the span of a portal. How? By drawing by modeling a beam perpendicular to the direction of the portal, that is from this point to this point. Number 13 is the main frame tapered column, or there's this one more thing that I want you to explain in this jack beam concept. Basically, sometimes it too happens that the client does not want a column here. It might happen that they want a free space here. So in that case also, we do make this jack beam arrangement here. Number 13 is the mainframe tapered column. So this is also called a mainframe tapered column. Number 14 is a cantilevered fascia frame. So here you will see from this point to this point they had made this cantilever fascia frame, so it might be used for holding any banner or for holding any signboard arrangement here. So a 15th is the lean-to frame. So this is basically a lean-to frame, that is single-sided frame. So this is only one sloping arrangement here, so that is why it is being called lean-to frame. Number 16th is the crane beam. Now this is also a very interesting concept, that if you have seen some various pictures of warehouses, or you might have been to some warehouse also, you might have seen these type of gantries or EOTs here. It is being called as EOT crane, that is electrically operated traveler crane. So the lifting capacity of these EOT cranes may vary from 2 ton to either 30 ton or 40 ton also on the higher side. So what exactly we as a designer need to do is that we may need to support this EOT crane on these columns here also. So and the purpose of this EOT crane is to lift anything from the ground and transport all the way, for example, from this point to this point. And how we can transfer from this point to this point, we usually provide some rail sections here. The rails are the same rails that are used to transport in the railways also. That is, you might have seen those sections and like this. So what exactly happens is that we do provide rails sections here, and on the top of those rails, with the help of the wheels, this EOT crane may move from this point to this point. But to support those rails, we do need some beams also. These are called the crane beams. And number 17 is the crane column. So this is basically called a crane column. That's this small thing here. So there's another EOT crane here from this point to this point. But what they had done is that they had supported this bigger EOT crane on the column on these portals here with the help of the crane beams. But they had made a separate arrangement, that is the sole purpose of this column is to support this crane beam. So that is why it is called a crane column, and it might be somewhat smaller in size, and the capacity of this crane must be in the range of 2 to 4 metric ton, not more than that. After that, the roof purlins that I had already explained here, that the purpose of these roof purlins is to support the sheeting arrangement on the top. Number 20 is the flange brace, that is this brace. Now this is also a very interesting concept here, that is why do we need to provide this flange brace here. So these are basically mostly the Z-shaped purlins here, and as an engineer, you know that the bending moment is directly proportional to the length of the member. I repeat, this is an important concept, that bending moment that gets generated in member is directly proportional to the length of the member. It can be either WL square by 8, or in purlins, as they are continuous, the bending moment is usually in the range of WL square by 10 to WL square by 12. So this flange brace, what exactly it does is that it supports the bottom of the purlin, or it breaks the free length of this purlin, and it makes the Z purlin strong. Number second is that it also supports the bottom flange of this main rafter here. So basically these rafters are made in the I sections. So there are basically two purposes of this flange bracing. One is to support this purlin, and second is to break the free length of this bottom flange of the section. So that is why the designers usually assign UNB and UNT parameters in the STAAD software also. UNB is the unsupported length of the bottom flange. UNT parameter is the unsupported length of the top flange. So that I will explain when we will model the PEB structures in the STAAD. But do remember this concept, and I shall also show you the detailed view or the drawing view of how exactly this flange brace can be made. So 21 are the sag rods. Sag rods are basically that I explained in the previous lectures also. So these sag rods are basically, the sole purpose of the sag rods is to break the effective length of this member along the minor axis, or to make this member stronger along the minor axis also. 22 is the eave strut here. So this is basically the eave strut. So This is called the apex. That is the topmost point. That is a general English grammar. So topmost point is called the apex, and the bottommost point is called the eave. Now the thing is, all these portals must be made stronger along this direction also. So in addition to the bracings, we also provide the eave studs, and sometimes we also provide the tie beams along this direction also, to make this arrangement strong and to tie all these arrangement along this axis also. Portal frame has a very high strength along this axis, along this direction, but all this system of all of these portal frames have very less strength about this direction. So to make these portals stronger along this direction also, we either provide the bracing arrangement or we do provide this eave strut on the top also. After that, 23rd is the side wall gird, that is this gird. So these the end wall girds and side wall gird do serve the same purpose, that is to support the sheeting arrangement. After that, this number 24. 24 is again the flush fascia frame, the same that we had made here. Now you should thinking, what exactly is this arrangement here? So usually along the PEB structures, they do make some RCC or steel composite structures also. They either use it as the purpose for office area or for this AHUs or to support the services. They do make this secondary arrangement also. So 25 is usually called the monkey ladder also. So 25 they had named it as cage ladder. 26th is the deck panel with steel mesh. So deck panel I had also explained in the previous lectures also. That is, we install a deck plate on the top of the structural steel sections. After that, we put some mesh reinforcement over that, and we do install the concrete slab over it. After that, 27th is nothing but handrail that has been made here. 28th is staircase that we can easily see here, and 29th is the crane bracket. So this is called the crane bracket. So basically, first of all, we make the crane bracket on the top of this portal. We make crane bracket. On the top of that crane bracket, we install the crane beams, and on the top of the crane beams, we install the steel rails. And on the top of those rails, this EOT crane is mounted. So this was basically the skeleton of the PEB structures. You can also see various type of warehouses on YouTube also. So to make the lecture short, I shall explain you only the important things. And otherwise, if you want to study this whole manual here, I'm sure at the end of reading this whole manual, you shall be very comfortable with PEB structures. They had given various definitions also in the beginning. So these are the various types of frames, and this is the suggested span of this type of frame. So this L canopy, it can be used in the range of 3 to 6 meter, in the range of 3 to 18 meters. So basically, obviously, the bending moment profile is like WL square by 10 or 12. So bending moment is higher on the top here and here on the bottom also. So that is why they had distributed this frame. The depth is more here and depth is lesser here. This is called a butterfly canopy. So the desirable range is in the range of 6 meters to 12 meter. Space saver arrangement. This is also an interesting concept that sometimes it do happen that, let us say the client do needs 12 meter clear height or 14 meter clear height, and if we want to go ahead with this type of arrangement, that spacing may reduce. So this space saver arrangement, what we can do is that, although we do require the higher depth in the bottom, so instead of increasing depth at the bottom, we do increase the depth at the top also. And this is the single slope. This is called a rigid frame. That is, bending moment is higher at the ends here and somewhat lesser in the middle. This is called the beam and column arrangement. Beam and column arrangement BC2, beam and column arrangement BC3, and this is called a multi-span portal arrangement here. So this type of arrangement can be used in the range of 6 meters to 36 meters, but not desirable in the range of 36 meter to 96 meter. That is highly what should I say, uneconomical gap here. So if you have something in the range of 24 to 60 meters, what we can do is that, let us suppose we want to go for 50 meter span. So at the end of 25 meter, we provide a column here, so that the whole 50 meter span gets divided into two spans, that is 25 meter both, in the range of 36 to 72 meters. So let us say if you want to go for 72 meter span, so 72 divided by 3, so 24 meter, 24 meter and 24 meter. Similarly, for 96 meters also we can provide 3 columns here, and in the range of 24 to 60 meters we can go for this multi-span arrangement here. Standard eave height, so this is called a eave. So this eave height is usually in the range of 8 meters. Most of the PEB structures that I have seen or I have designed them in the range mostly for a clear height of 8 meters or less or more. So standard base spacing is usually in the range of 6 meters, 7.5 meter to 9 meter. It is most economical in the range of 7.5 meters, somewhat less economical in the range of 6 meters and 9 meters. So the most desirable base spacing also is in the range of 7.5 meters. After that, standard loadings for live load, we can apply 0.5, 0.6 or 1 kilonewton per meter square. So live load is usually given by the design codes only. So it is somewhat lesser for the American standards, that is they do provide the live loading requirement of 0.57 kilonewton per meter square. But Indian standard do guides us that we do need to take 0.75 kilonewton per meter square, reducible as per the slope of the PEB shed. Wind load can be in the range of 0.75 to 1 to 1.25 or 1.75 or 2 kilonewton per meter square also. It all depends upon the area in which that PEB is being built. So this is the loading arrangement at a single gable building. Here we can see that this is the dead load plus live load. So as I discussed, that live load is usually taken 0.56 kilonewton per meter square. Wind load can be taken 1.25 kilonewton per meter square uplifting only. So this is the lifting arrangement or suction of wind load, and it can goes like this. And GCP minus GCPI, so G is usually taken as 0.85 as per the American standards. So all these factors you can take from ASE, or if you are comfortable with the wind load calculations, you can calculate the wind loading arrangement easily. This is called the single slope building. This is the T canopy, L canopy. So standard building arrangement, what we do is that if let us suppose if you want to make a building of 18 meters width, 18 meter width by 48 meter length, we can consider eave height of 8.5 meter, and base spacing we can consider 8 into 6 meter, that is 48 meters. And project number they had also referred to the here as page number 242, so that we can discuss later also. So this is the bracing arrangement, standard cable bracing arrangement. So as I had discussed with earlier also, that these members can only be taken as tension member, because cables or wires do not have any compressive capacity. So they are usually somewhat pre-tensioned also. And this is a hillside washer, and this is nut and washer arrangement. And with the help of this washer arrangement, we usually tie this cable arrangement here. So these cables are usually made of high strength steel and usually of yield strength 345 to 415 Newton per mm square, and they are usually taken a diameter of 12 mm or 16 mm or 20 mm, not more than that. So as they had discussed that they are always in tension. This portal frame bracing arrangement that we had initially discussed also, that they can be act as substitute for the cable bracing arrangement. Knee bracing also we had discussed earlier also, that is when the diagonal bracing is not allowed in sidewalls because of excess, we can use this knee bracing arrangement. And after that, diaphragm bracing system also, and this is a standard eave canopy that they had explained here. So this was the fascia arrangement that they had shown here. This is an arrangement of how we can make the expansion joint at the roof, and they do assign this separate expansion panel on the top here. This is for the expansion joint at the wall. This is standard end wall system arrangement here. So This is a typical arrangement showing the I section arrangement with the anchor bolts. So this is basically called a pinned connection. So most of the pre-engineered buildings are usually designed in the with the base as pinned connection, and only 5% of PBs, I must say, are designed taking the base as the moment connection. So this is called the rigid frame. So as I had explained earlier also, that this is basically the crane beam, and on the top of that crane beam they had installed this crane rail, and on the top of that this EOT basically runs on the wheels. This is a practical example of a EOT crane. So here you can see this is the crane beam. So here this is the multi-span braced frame. Multi-story steel buildings are also existing worldwide. Mezzanine flooring system. So here you can see that this is the mezzanine floor, and on the top of this mezzanine floor they do install the deck panel or deck sheets. On the top of that they do the concreting, and on the top of that they had made some PB arrangement here. So these are the open web steel joist. So I had explained joist arrangement earlier in the earlier lectures also, that basically we do take help of the this higher depth, and with the help of this higher depth we do distribute the forces into the axial and tensile forces only, reducing the bending moment in the beams. So this is the basically open web steel joist, and you can refer to SJI codes also, that is this is basically the main frame, and this is the arrangement with which we join the steel joist with the help of this main frame, with the help of this shoe clip. And the advantage of this steel joist is that we can reduce a lot of steel. In addition, we can easily pass on the services also. And if you have been to some airports also, so most of the airports, if they are usually made in a pre-engineered building system also. So here you can see that this is a hangar, and in that hangar they had made this pre-engineered building arrangement here. These are some examples special fascias that they had protruded outside the special fascia arrangement here. This is a typical arrangement of a built-up roof. So what they do is that they install the steel beams here. On the top of the steel beam they install the joist, and on the top of that they install the Kirby deck system, and on the top of that Kirby deck system they do install this vapor barrier and insulation panel, because sometimes it do happens that we do need to provide insulation to the bottom. Insulation is usually from the outside temperature, so we can provide this insulation panel. On the top of this insulation panel we can provide the concrete slab, and on the top of this concrete slab we can provide this waterproofing arrangement. It can either be with the help of this alternative layers of bitumen and FELT and gravel or slag. So this is showing the typical waterproofing arrangement on the top. Yeah, this is a very good example of roof monitor system. So basically sometimes it do happens that we do need some natural lighting arrangement, or we may need the ventilation from the bottom also. So what we need to do in that case is that we can provide a secondary portal on the top of this master portal, main rafter here. So we can see that this is a main rafter. On top of that we install the sheeting, and we had stopped the sheeting at up to this point here only, and here they had provided this flashing to prevent the rainwater from entering, and here they had provided this bird screen so that birds does not get inside this whole building arrangement here. And in addition, usually this angle is usually in the range of 60 degree here. Here they had provided this another eave flashing and eave strut, and this is a roof monitor, and this is basically the peak panel. And if you have been to various metro stations also, so here they can usually to provide this arch system as the portal arrangement. So the advantage of this arch system is that you must have studied the various type of arches in your college studies, that is 2-hinge arc or 3-hinge arc. That is, they do decrease the forces a lot. So this whole arrangement is itself a very stable arrangement. So here you can see that in the workshop they are making this curved beams here, and flanges can range from 125 to 5 mm to 400 by 16 mm. Depth can range from 200 to 12 mm. And here they had made this curved aircraft hangar in Yemen. This is in Bahrain. Here they had explained about the secondary members. So most of the secondary members are made in the cold form steel structures. So this is a Z purlin, E strut and C section. So this is a typical diagram of a Z purlin arrangement. Here that is height, that is 200 250, and mostly that thing that matters is the thickness of this. So T can be either let us suppose 2 mm to 3 mm or 1.5 mm also. So this is the typical arrangement of a E strut. So here they had given the various areas: weight, slope, allowable shear force, allowable compressive force, and here also they had explained given the elastic modulus and allowable moment in these cold form C sections are here. So this is basically the Kirby rib, roof and linear sheeting section properties and load tables. So here they had given the allowable loading also. So this is basically the typical example of a Kirby deck panel arrangement. So the yield stress is usually in the range of 345 Newton per mm square, and steel panel thickness is usually 0.7 mm. And here they had given for various span the allowable uniform load. That is, if we are considering that deck panel type of 1.6, and we can consider the 3.72 kilonewton per mm square. And deck panel must be designed to withstand concrete net weight plus 0.05 kilonewton per meter square construction load. So this is also sandwich panel. So these are the various sections showing the insulations. Insulation is a very important concept that most of the people are not comfortable with. Insulation are basically these are the panels that are itself embedded in the panels to insulate the exterior environment from the interior environment. So basically you can see that this is a fiberglass insulated panel for roof and wall panels, and thickness can be in the range of 50 to 60 to 70 mm, and maximum working temperature, fire safety, acoustics, all these are given here. These are self-draining screws. Basically when we want to install the purlins on the top of the main rafters, so in that case we do install this self-draining screws. So head can be either in the range of 9.3 to 9.52 mm. EPDM washer diameter is usually in the range of 19 mm. These are the pull-out strength of these anchors. So when we are considering 1.5 mm thickness purlin, so ultimate pullout is only 1.16 kilonewton. So these are the self-draining screws that make sure that in the case of extreme winds, when the roof just want to get out or just want to get blown in the air, so in that case these screws are the thing that grips the sheeting to the purlins. This is a typical example showing the cable bracing. So they are usually made of either 836, and they are lightweight and economical. This is basically the section showing the anchor bolt arrangement. So anchor bolt arrangement that I had already explained few minutes back, that the anchor rods are the rods that helps to transfer the loading arrangement from the PEB portals to the pedestals and ultimately to the foundations. So here they had given the bolt diameter and appropriate length and pitch and center to center spacings, and they had also given the allowable shear and allowable maximum tensions, etc. So they had also explained about the HT bolts. Here they have seen the ASTM 825 high strength bolt, HS bolts. So now they are explaining the crane beams sections here. So the ventilation is also a very important concept when we are designing the PEB structures. So although these are the separate consultants that do all the ventilation calculation and insulation calculations, This is a nomograph showing the ventilation calculation for the typical arrangement. Roof lighting requirements is also sometimes considered. That is, if the day light is more, then we don't need this roof lighting arrangement. But if the daylight is less, then we do need the lighting arrangement. There they have done typical calculations also. For example, let us suppose if the daylight factor is 6%, so net area of lighting required is 205 meters square, and net area of one light is 3 meters square. 205 divided by 3 is approximately 70 numbers of skylights are required. Roof drainage. Drainage is also a very important concept when we are designing the PB structure. That is, whenever the rain falls on the top of the PB roofing arrangement, then we do need to make sure that we do need to design the gutter arrangement also and downspouts also. Downspouts are the pipe which transfer the water from the gutters to the below drainage. So fire protection system can either be in the form of this fireproofing paint or some special arrangement here. So here they had considered pre-mixed factory pre-mixed fire resistant coating, Mandoval P20 or equal can be applied. So this is the fireproofing arrangement that you can see here. So here they had given the some building material weights also. So conversion factor, we all know that approximately 1 foot is 0.3 meters and all these simple calculations. Here they had given the minimum dimensions for the aircraft hangar design. This is simple walk door arrangement. This is a typical sliding door arrangement. Sliding and folding door. Sliding and folding door is usually used for hangar structures. And this is a typical material specifications. This is again showing the insulation. This is a typical slidable window. Here you can see that these windows can get sliding. Yeah, this is a lure that we were discussing earlier also, that it basically solves the purpose of the this ventilation. And this is a sand trap lure. This is translucent panels. So here you can see that basically the light is entering here, and how light is entering here at this point is that we had provided the translucent panels to allow the daylight from outside to enter the inside. So the translucent panel thickness can be either 1.5 mm, covering width, etc. They had all given all the data here. Thermal transportance mu value also they had given, that is 5.7 W per meter square. Linear thermal expansion coefficient they had also given. These are the ventilators. So on the left is a ridge ventilator. This is basically the turbo ventilator option, powered ventilators. So ventilators are also usually installed for the PB structures. This is called a gutter. So initially we were discussing about the rainwater exit. So this is a typical section showing the gutter arrangement. So basically the rainwater comes here, and on from this they do get collected into the downspout pipes. So here they had given the possible location of the downspouts. So they had drawn 4 downspouts arrangement here, and they had given the typical downspout spacing also. So this is a valley gutter downspout, because basically when we are talking about the 2 PB structure, then rainwater must get collected here. So for that they do provide this valley gutter arrangement here like this. And this is basically showing the Kirby M liner. Light partitions. So light partitions are like, we don't usually do the brickwork inside the PB structure, we do provide the light partitions. So in that case we can provide the gypsum board panels arrangement also. This is a typical section showing the false ceiling. So these are the false ceiling panels, and from these false ceiling panels are basically tied to the top of the PB shed with the help of these galvanized wires. So all these loadings we must consider in our designs also, that is whether there shall be false ceiling or not. If there is false ceiling, then we should take the optimal design load in our PB designing. So this is showing the basically Z purlins with the help of this bracing arrangement and wall details cable. Yeah, this is showing the clear arrangement of this purlin gird connection. So here we can see that this is basically the I section here. This is the bottom flange, this is the top flange. So top flange is also tied here with the help of this purlin, and bottom flange is also tied here with the help of this purlin, with the help of this flange brace here. So we usually do provide this M12 bolts or M16 bolts or M10 bolt here as per the design requirements. This is a typical detail at eve arrangement. This is a gird connection. So when we want to join the gird with the help of this, so what we do is that we provide a clip section here. So at that, with the help of this clip, what we do is that we anchor this gird arrangement with the help of these two bolts here. So this is also typical arrangement showing the bracing details. So all these are typical sections showing the bracing. This is a simple arrangement to show the window, and these are the vertical fascia details, vertical mansard details, conventional mansard details, roof framed opening detail. How we can provide the roof opening with the help of these rearrangement of the purlin sections only. This is a typical arrangement showing the walk door, single slide door, double sliding door, double folding doors, roll up doors, or they are also called as rolling shutters or rolling shutter arrangement. So here you can see this is a chain pulley arrangement with the help of that we can easily roll the shutter, roll up door, hanger door details, crane system details, mezzanine details. Staircase are just like we make some channel sections here, and from those channel sections we do provide this clip section, and on the top of these clips we can either do the 6 thick plate that can be get welded to the joist here, and here they had taken 250 into 100 into 3.5 channel stringer arrangement here. This is a wall panel downspout. There are endless number of details here. You may fall short of time, but you shall not fall short of the data that has been given here. There are a lot of sections here that has been drawn here. This is standard structural system of a building that has been made here. So here we can see that they had given the plan bracing also here. They had drawn the base plate arrangement here. Here they had given another typical framing arrangement here. So there is a lot of standardization work also that has been done by Kirby and Zamel, and there are a lot of research work also that has been done by both of these companies. So in the previous lecture we had learned much about the basics of the PEB shed, how and what are various parts of the PEB sheds and how they are used in the real life. So now as a designer you may have an assignment in which you may need to design and you may need to analyze a pre-engineered building shed. So to do that, what we can do is that first of all we start our start software, and here enter the units as meter and kilonewton, and enter the joint coordinates as 1, 0, 0 and 0. That is the origin. Now first of all press Shift plus K to expose the node. Now press Ctrl C Ctrl V option on your keyboard and select YS 8.8. So this is the height of our PEB shed, and we can enter or we can model a beam here, we can model a column here. After that what we need to do is that we need to make a portal like this. So to make a portal like this, what we need to do is that we need an apex point also. So let us suppose if we want to design a PEB shed of 36 meter span, so that is approximately 120 foot. So what we need to do is that we can press Ctrl C Ctrl V again and select X here as 18 meters. So now if we want to model the slope of this PEB shed, let us say the slope is 1:10. So this distance is 18 meters. So as a simple math, we need to divide this value by 10. So this nodes needs to be up by 1.8 meters. So this is a simple half portal here. We can delete this beam here. After that, what we need to do is that we can just simply mirror this column about this beam here. So go to this generate mirror option here, select the plane as YZ, node as this, and select copy here. So we can simply draw this portal here. Now as a basic understanding, this is an example that you must have solved in your college lectures or your college examinations also. So this is just a simple portal that we are talking about. Now further, there are two concepts here. Most of the old PEB people, what they do is that they just simply model the portal and then analyze and design the structure. But nowadays, with the invention of new softwares and with the introduction of various high level analysis software, what we can do is that we can simply model the full pre-engineered building shed or pre-engineered building warehouse, so that we can check and we can analyze and design the forces and bending moments along both the axes, that is along X as well as along the Z. So my preference is also that we should always go for the three-dimensional analysis of the PEB shed, as there's no purpose of doing the 2D analysis when you have such an advanced softwares. So now the next thing is that we need to break this portal also. And how we can break this portal here? This distance is approximately 18 meters. So we can left click on insert node, we can add n 3 points, and then left click on OK here. Similarly, insert node, add n points and 3. Now you must be thinking why we are breaking this beam into various parts. So if you remember your lectures correctly, what the thing is that the height of this beam varies. That is, the height of this beam is maximum here because the bending moment is maximum here. After that, it somewhat reduces here, and then it again increases here because here this is the negative bending moment that is maximum, here this is the positive bending moment that is maximum, and negative bending moment is approximately much higher as compared to the positive bending moment. Now we can also break this beam here, break this column here. So we can left click on insert node, add midpoint, and then left click on OK, so that we can easily increase the size of this beam here. Now we need to go to general and property. We can left click on define here, and then left click on tapered eye section. So this is the option with which we can model the PEB sheds easily. And here you can see that this is the depth of section at start node, and this is the depth of section at end node. So if we want to take this depth here approximately as 900 mm, so we can enter 0.916 here. Thickness of web we can enter it as 8 mm. Depth of section at end node. So let us say if we want to decrease the depth of this beam from this point to this point from 900 to 700. So what we can do is that we can enter 0.716 here. Width of top flange we can enter 0.25. Thickness of top flange we can enter it as 20 mm. And width of bottom flange again we can enter 0.25, and thickness of bottom flange we can again enter 0.020 mm meter. So left click on add here. So press Ctrl+2 option on a keyboard. So here you can see that basically the thing is that this is correct from this part, that is this is the starting joint and this is the ending joint, but here this is inverse. So what we can do is that we can simply select these beams here and go to tools, redefine incidence, and switch incidence of selected beams. So now if we check the 3D here, so here you can see that the depth is maximum here and the depth is maximum here. After that, if we want to again decrease it from 0.716 to, I guess it should be comfortable at around 0.516. Thickness of web we can take it as 8. Width of top flange we can enter it as 0.25 only, and thickness we can enter it as 0.016. So left click on add here and then assign to selected beams. So after that, what we need to do is that this is the minimum thickness, it is 500 mm. After that, again we need to increase the depth here. So again we go to define, taper die, depth of section at start node 0.516, thickness of web 0.008, 0.616, width of top flange we can enter 0.25, 0.016, 0.25, 0.016. So now the depth has increased from 500 mm to 600 mm here. So if you want to increase depth from 600 to 750 mm here, so again we need to go to define, taper die, and 0.516 to 0.766, thickness of a 0.008, width of top flange 0.25, 0.016. Now you must be thinking why we are entering 16 mm here, because the thickness we are considering it as 0.016 mm, so it doesn't it doesn't have much difference. But as the stat consider it as center to center distance, so we can do it like this. But if we want to go ahead with values like this, then you are 99% correct. But it is always suggested that whatever thickness of the flange you are considering here, enter here, because we are considering center to center distance here. So this profile we can consider here, and in the initial we had considered 20 mm thickness, so we can take it as 0.920 and 0.720. So this is the three-dimensional view of the PEB portal that we have drawn. That is, maximum bending moment is here, so we had considered 900 mm, and somewhat lesser bending moment is here, so we have considered 750 mm here. So the bending moment profile shall be like this. For this is the span is very much high for this PEB shade. So after that we can draw this column also. So we can go to define, taper die, thickness, depth of section start node. Usually the depth of flange at this point, depth of web at this point is approximately 300 mm. So we can enter it as 0.316. Depth of section at end node we can take it as 0.566 or 0.516. Thickness of web 0.008. Width of top flange 0.25, 0.016, 0.25, 0.016, and then left click on add here. And as we have taken the depth here as 0.516, so we need to increase the depth from 0.516 to 0.766, or usually it should be around 0.916, because whatever bending moment is here, that same bending moment shall be balanced on this part here also. So thickness of we can 0.008, thickness of 0.25, 0.02, 0.25, 0.02, and in this we can take it as like this. So this is a simple portal that we have drawn. After that, properties have been entered here. Specification, we don't need to enter anything for this portal arrangement here. After that, support, usually the PEB sheds are made as a pinned support only. So this is the typical portal, or this is the typical portal of the PEB warehouse structure that we have modeled here. After that, what we can do is that we can just simply select this whole structure here, select translation repeat, and select global direction as Z. Default stress spacing we can enter it as 6.4. Number of steps we can take it as 6, and then just left click on link steps here. So after that, what we need to do is that we need to delete the beams at the supporting level, and after that we need to draw the bracing also. So we can just simply brace the starting point as well as the ending point. Or what we can do is that there is this one more thing that you should know. This whole area, either it can be left open, or most of the times what it usually the case is that we do need to model the wind columns also. So we can just simply draw a beam here. We can go to geometry, add beam by a perpendicular intersection. So similarly we can repeat this whole structure at 38.4 meter distance also. So we can select Z as minus 38.4. So these are the wind columns that we have modeled here. So now the main portals, main rafters and the main wind columns have been modeled here. After that we need to give the supporting conditions also to these wind columns that we have modeled. So now the wind columns have been modeled, rafters and everything has been modeled. Consider this as a tie beam here. That is basically the thing is that this rafter that we are talking about here, this rafter is very strong along this axis, that is along x axis, but simultaneously it is very weak along this axis, and many failures have also occurred while constructing or while in the erection stage, that if the contractor does not brace this portal sufficiently along the perpendicular direction, then it has also happened that this whole arrangement has come down or it has failed along the perpendicular direction. So to brace the structure along the perpendicular direction, what we need to do is that in addition to the ties that we shall provide, we shall also provide additional bracings also. So this bracing is also a very important concept. Some of you must be thinking that where and how this bracing should be provided. So as a thumb rule that you should know, bracings are always provided along the weaker axis. There is no logic in providing the bracing along the stronger axis. So here you can see that this is the weaker axis that we are talking about here. That is, whole moment of inertia is about this axis. So that is why we are providing this bracing here. Now this bracing is also somewhat different approach with the different engineers. Different approach means that some people take it only as the tension members. They only model this bracing as a tension member, assign 12 mm or 16 mm rod to these members and then design them. So what they do is that they assign this bracing as a tension member, so that only tension force will travel in these steel structures. As you can easily guess that 12 mm this rod has a very negligible compressive strength. So for that, what they do is that they model this whole bracing and assign them as tension member and then appropriately design them. So now it's up to us that whether we can go ahead with this define and circle. Here we can enter 12 mm rod and then assign to all these members, but my personal experience is that I never provide this rods as the bracings, cause that is just a behavior to save the structural steel from the PEB vendor side. So some of the experienced engineers that must be listening to this might not be comfortable with what I am saying, But according to my concepts, what basically the thing is that we should always provide bracings as a either compression member, or it can be as a tension member, both, because we shall never know how in earthquake this structure will behave. That is, the structure may go in a torsional mode also, the structure may go in a translational, or the structure may go in a linear translational mode. So it's all up to the behavior, that how earthquake force will strike this structure. So as a my experience, I always go ahead with either pipe section or either go ahead with channel sections, so that the bracing can bear both compression as well as both the tension forces also, because this structure is very small. Here we are only talking about the 40 meters, but when we are talking about the 80 meters or 100 meters, even the tensile force, the temperature forces are also very high, so they may also cause the compressive or tensile forces in the bracings also. So as a piece of advice, if someone asks me that whether I want to go ahead with this rods, or either we want to go ahead with this circular hollow section or channels as a bracing, I shall always answer that I want to go ahead with channels or circular hollow sections as a bracings members. So after that, we can go to this define, or we can go to section database here. We can go to this Indian, and we can go to the pipe section here. So here we can select 1016L. Basically this is a 100 mm pipe with 4 mm thickness, and left click on add here. So we can select all of these members here. So now this PEB shed has been modeled, all the properties have been assigned, but the next thing is that we need to go to define tapered eye, depth of section start node 0.3, end 0.3, 0.008, width or top flange 0.2, 0.012, 0.2 and 0.012, and then left click on add here. Now we can assign this property to the wind columns here. We need to check the orientation also. So we can press Ctrl+2 option on a keyboard. So here we can see that the orientation is not correct. So we need to rotate this orientation here. We can go to commands, geometric constant and beta angle, and here we can enter it as 90 degree. So now the wind columns have been correctly modeled. After that, there is no logic in making this member and this member same. So what we can do is that we can go define tapered eye, depth of section start node 0.3, 0.008, 0.3, 0.2, 0.012, 0.25 let us say, and 0.012, and then left click on add here. So for the end, gable end here, we can provide the reduced size. After that, usually the case is that this column is also the requirement is not heavy. So what we can do is that we can assign this property to this member also. We can increase the size of this member here, because it's looking very small. So I am just guessing the sizes of these members, and we shall see that whether they shall pass in the final design calculations or not. After that, we can go to the section database here. So we can go to the cold form steel sections here, and here we can select the either American cold form or Indian cold form. Here we can select this Z or Z with lips. So this cold form steel structure I already explained in the previous lectures, that what exactly are cold form steel structures, and how basically these members can be either modeled as the channels, or they can either be provided as the form of the purlins also, because purlins are the members that tie this whole PEB shed along the weaker axis or along the perpendicular directions. So we can select here the (200Z as 61.6). It means that the height of this Z section is 200 mm. The flange the width of the flange is 60 mm, and the thickness of this whole section is 1.6 mm, or we can go ahead with 2 mm also. So we can go to select by missing attributes and missing property, and then assign this property to all the members here. Please note that we shall not design this purlin section here. We shall design these sections manually, and the side purlins, also called girts, we shall design them manually, but not in this video lecture. So I shall only focus on this software modeling, software analysis, software design. Otherwise the length of this course shall be too much. So to avoid going into the further details, what we can do is that now this whole PEB shed has been modeled. We can check that in the 3D view also, that this whole PEB shed has been modeled correctly or not. The orientation is also very important here, as I had requested you earlier also, that we do need to check the orientation of these wind columns here. And bracings also we have modeled. So in the next lecture we shall start with the load cases and load combinations as per the Indian standards. So in the previous lecture we have learned how we can model a PEB shed. Now in this lecture we shall learn how we can apply the loadings. So before applying the loading, let us do a minor change in the modeling that we had done in the previous lecture. Let us make it more interesting. So to make it more interesting, or to, what should I say, that I want to give you somewhat more practical exposure. Let us suppose the client says that he wants this distance not to be 18 meters but somewhat more than that. So the total, keeping total as 36 meter, let us say that he wants this distance to be approximately 18.5 meter and this distance to be 17.5 meter. So in that case what we can do is that we can select this whole column here. We can go to geometry, move, joint, here select x as 0.5 and then left click on retain connections. So here we can see that this distance has now changed to the 18.5 and this distance has now reduced to 17.5. So the apex point has shifted, or the apex line has shifted by 0.5 meter along the positive x direction. Now we can left click on the seismic definition option here, and before that, to make it more automative, so my recommendation is always that we should always do the hard work in the beginning, but after that we should always try that we should make some shortcuts, or we should make some ready-made load cases or ready-made pattern that we can just copy paste into our editor file, so that we can save a lot of time. So to help you with that, I had prepared this notepad file for you that I had attached in the lecture also. So we can just simply copy paste this whole arrangement here, left click on copy and just go to the editor file here, and after supports just paste it and press save option on your keyboard. So here we shall see that simply all the load cases has been just copy pasted here. So instead of manually entering all the data here you can see that now you have got the ready-made data that you can just use and save a lot of time. So I want to beef up everything to you. So here we can see that the first load case is seismic plus x, seismic along minus x direction, seismic along plus z, and seismic along minus z direction. Dead load, we can enter self-weight as minus 1.05 to account for the connections weight also, or to account for the miscellaneous fixtures that shall be added in this pre-engineered building shed. So live load we can also enter. This is the wind load along left, and considering CPI value. So for those who are not conversion with the Indian standards, basically CPI value has been classified for partially enclosed, enclosed and open structures. So the values for those or for those enclosure conditions is 0.2, 0.5 and 0.7. So in this case I am considering 0.2. So I shall explain everything about wind load also, that what are the provisions for application of wind load as per the Indian standards. But before that, we were discussing about this whole load cases here. So this is wind load from right direction, keeping minus 0.2 CPI only. So this bracket value is nothing but CPI, that is internal pressure coefficient. And for external pressure coefficient, we shall refer to the Indian design standard or the values that has been entered. So we shall, for those who are not using the Indian standard but are using the American standards, so I shall explain that also in the separate lecture. But for the American standards, the mostly the practice is that we follow the MBMA design manuals, that is Metal Building Manufacturer Association design manuals. So you can simply Google that to know about the MBMA manuals. So my experience with the pre-engineered building designers is that most of them uses the MBMA only, because MBMA derives its value from the ASCE 07 only. So more or less both the tables or both the values are same. And coming back to this lecture here, so this is wind load minus 0.2 from left to right, and this is from this right to left. So basically the we must be thinking that why we are taking two values for minus 0.2. So I want to explain you here that this thing here, that is this dimension is 18.5 and this dimension is 17.5. So obviously we do need to consider that in the case where wind is traveling from this direction, so from this point to this point the loading shall be different, and from this point to this point the loading shall be different, because this length is different here. So this was the reason why I had shifted this 0.5 meter here, so that you can have a practical understanding of what if this portal and this length is unequal. So if both of the length are equal, there's no use of splitting this and this, cause in that case we are just simply wasting our time. But if this dimension and this dimension is different, then obviously we do need to take model this 1 2 3 4 5 6 7 and 8. So this is the longitudinal direction along from left, wind load along longitudinal direction from right, and this is the longitudinal direction from left with plus 0.2 plus EPI, and similarly from right this is the perpendicular direction, that is with perpendicular direction as minus 0.2 and plus z, minus 0.2 and minus z, perpendicular plus 2 and plus 0.2 and plus z, and perpendicular plus 0.2 and minus z. After that, as per the earthquake requirements, we do need to take care of this 0.3 option also, that is ELX plus 0.3 ELZ, ELX plus 0.3 EL minus Z, and all these things here. So here we had considered ELX plus 0.3 ELZ, ELX plus 0.3 EL minus Z, ELZ plus 0.3 ELX, and ELZ plus 0.3 minus EL minus X, or minus 0.3 plus ELX. So these four options can be taken here. After that, we have also entered the load combinations also. So this load combination nothing but 1 times dead plus life. So right now we are talking about the working stress design, not limit state design. So that we shall enter in the design parameters also, that we want our design as per the working stress design also, or WSD. As per the American standard, it's called AST, that is allowable stress design. So that also we shall discuss in the separate lecture. But coming back to this lecture here, so you can just simply refer to these load combinations here. So you must be thinking what exactly it means, that P right to left or P left to right. That P means the pressure and S means the suction. So basically wind shall have two types of effects. Either it will cause the pressure effect or either it will cause the suction effect, depending upon the coefficient. That is positive values means that it is acting towards the structure, and negative value means that it is acting away from the structure. So this point is also very major confusion among the most of the students, that what exactly it means. That is, when the pressure value is negative, as a simple thumb rule you should always remember that whenever the CPE minus CPI value is negative, it means that the loading is acting away from the structure, and positive, it means it is acting towards the structure. So we shall also discuss this Excel file also here. That so in this Excel file it is clearly written that that positive wind load indicates the force acting towards the structural element, and negative indicates that it is acting away from it. So here we can see that this is the negative force, so it shall act away from the structure, but this is a positive force, so it shall act towards the structure. So jokingly I should say that if I do something wrong, then don't get confused in this, because sometimes it do happens that wind load may become negative, and people what usually do is that they apply it towards the structure or vice versa. So coming back to our Excel stat file here. So all these load combinations you can refer it from your end. That is pressure from right to left, suction from left to right, and suction from right to left. And this is the pressure along longitudinal plus Z, and this is suction along longitudinal plus Z direction. That is, we are considering the wind load perpendicular in the perpendicular direction also. So all these things are very interesting, but you only need someone who can just simply explain to you all these things, because it becomes very difficult for a unexperienced engineer to understand all this, or for an graduate student to understand all of these concepts. So I shall request you to read this wind design course, or to see various calculations that are available free of cost on the internet, to understand how we can calculate the wind load as per the various design standards. So coming back to this lecture here, so now in the next lecture we shall discuss how we can assign the seismic parameters, how we can calculate a dead load, live load, and wind load, and how we can complete all these load cases, and then finally we can assign the design parameters also. So in the previous lecture we have already learned that how we can enter the load cases and load combinations. So first of all, we shall start with how we can enter the dead load and live load values. So for this structure, what can be the dead load? The dead load can be the sheeting over the top of this whole arrangement. Dead load can be if we are installing some ventilators, turbo ventilators, etc. It can be the weight of the insulation that is usually installed on all the four sides of this type of structure, or it can be the weight of the solar panels also. So although that comes under the classification of collateral loading also, but in this arrangement I have not considered the collateral loading differently or separately. So coming back to this sheet here, so here we can enter the length of the building as 38.4 and the width of the building is 36 meter. So this is 38.4, width we can enter it as 36 meters. Purlin spacing is we can enter it as 1.5 meter. Base spacing is the spacing between this portal and this portal here. So this is 6.4 meter. So 6 into 6.4 is basically 38.4 meters. So base spacing for gable end we can enter it as 9.5. Although this value is not used anyway, but just for your records, clear eave height is 8.8. and maximum eave height we can enter it as 10.58. so this height is approximately 8.8 meters. So 8.8 plus 1.8, it comes out to be approximately 10.6. Roof slope, we can enter it as 10 degree here. So this is already the consideration that we had taken in the beginning. So dead load can be the weight of the sheeting, purlins and sag rods. Usually this weight is in the range of 15 kg per meter square only. So but 15, and collateral loading is also a separate arrangement here. So collateral loading can either be in the form of HVAC, that is ventilation that we usually provide inside the buildings. It can be the weight of the services, or it can be the weight of the fireproofing or solar panels, etc. So instead of collateral loading, what we can take is that we can combine dead load and collateral loading in one possible load case. So we can take it, the weight here is 25 kg per meter square. So for center span, it is nothing but 25 into the 6.4 meter. 6.4 meters. So the value comes out to be 1.6 kN per meter. So we need to apply UDL of 1.6 kN per meter and 0.8 kN per meter on the gable ends here. So we can select all of these members here. We can go to view and selected objects only, and for dead load, we can enter the weight here as member load and minus 1.6 kN per meter. Then left click on add here, and then just simply select all the rafters here, and we can go to the labels, scales, apply immediately and distributed force. So here we can see that the UDL has been applied correctly. So meanwhile, we can also calculate the live load for this type of structure. Live load is 75 kg per meter square, but please note that this live load is reducible as per IS 875 part 2. So conservatively, we can take it as 75 kg per meter square also, but if we refer to the Indian standards, we can see that this live load is reducible as per a particular formula that has been given. So for this here it is saying that sloping roof is slope greater than 10 degree. So for roof membrane sheet or purlin, 0.75 kN per meter square less 0.02 kN per meter square for every degree increase in slope over 10 degree. So subjected to minimum of, we cannot reduce this live loading less than 0.4 kN per meter square. So in our case, it is only 10 degree. So we are bound to use the 0.75 kN per meter square. But in your practical assignments, if you get a slope, let us say of 15 degree, then you can reduce 15 into 0.02. That is 0.3 kN per meter square. So 0.75 minus 0.3, that is 0.45 kN per meter square. So for 15 degree, we can use the live loading of 0.45 kN per meter square. So in our case, we shall go ahead with only 0.75 kN per meter square or 75 kg per meter square. So for center span, it is approximately, ignore this number here. So and for gable end, it is obviously 50%, because the effective span of this rafter here is 50% of this and 50% of this. The 3.2 plus 3.2, that's 6.4 meter. But for the gable end members here, it is only 50% of 6.4, that is 3.2. That is why we take 50% of loading whatever we are assigning here. So first of all, if we want to close the case of the dead load here, we can go to the member load and we can enter minus 0.8 kN per meter here. So we can select all the members here, left click on assign to selected beams, and yes. After that, we can go to the live load section here, and here we can enter the member load. Here we can enter the loading as 4.8 and 2.4. So we can enter minus 4.8 kN per meter, and then we can, from the editor list, we can just simply copy paste this member here. So press Ctrl C and Ctrl V here, and after that, for the gable end members, we can enter the member load as minus 2.4 along the global y direction. So we can just simply copy paste this whole members here. So now we have correctly assigned the dead load also, and now we have correctly assigned the live load also. After that we can refer to the wind load sectionals also, and before wind load we can also assign the seismic parameters also. So for here we can go to the seismic definitions. Here we can select IS 1893 and 2002 zone. Let us say we are working in zone 4. Transformation factor we can enter it as 4, I1, SS2, ST2. So when we left click on generate here we can refer it as zone. Let us say zone 4 we are talking about. We are talking about steel frame with concentric braces, because all these bracings are concentric. So R is 4. This is general building. We can enter it as medium soil. Structure type we can enter as steel frame building. Damping ratio 5, and period next we can enter it as 0.5 only. So left click on add here and then enter sulfate as 1. Now this period we can calculate it as per the 0.085 h to the power 3 by 4 also. So height we can take it as 10.6 to the power 0.75 into 0.085. So it is coming out approximately 0.499 or 0.5 seconds only. So we can refer to the period as 0.5 seconds. And after that we can enter the these loadings also. So considering 0 probability when the earthquake comes, there shall be loading on the top of this PEB shed. So we can only enter this dead load cases only. So we can go to the editor file here. So here we can enter this dead load as member load, and we can just copy this whole arrangement here. Here we can enter it as member weight and uni 1.6 and uni 0.8. So here we can see that this 1.6 and 0.8 is copied here. So after that dead load and live load is assigned, but after that we also need to assign the seismic load cases also. We can go to the seismic load option here, select X, and for plus Z select the seismic load and select Z direction here. After that we can go to seismic minus X here, seismic load, and X as -1 here. Similarly for minus Z direction also we can go to seismic load, Z as -1 here. So now all the seismic load cases has been defined, and after that what we can do is that we can go to this perform analysis and we can go to change. So press Ctrl C and Ctrl V. Again copy paste this arrangement here. So this is just done to ignore the warning that if this UBC analysis is tension and compression. So if you are a seasoned user of STAT, you must have got this warning that in the output file it says that if this UBC analysis is tension and compression. So to avoid that warning, we enter this perform analysis and change command, and this thing has already been explained in the many times in the previous lectures also. So now the seismic load cases and seismic parameters have been assigned correctly. Now after that we should touch our elephant, that is how we can assign the wind loading option in this PEB shed. So before that I want to explain the wind loading parameters also as per the Indian standards, and I have an understanding that if you are clear about how we can calculate wind load as per a particular country standard, then you can easily understand how we can assign the wind loading as per the various other country standards also. So more or less the approach is same. That is, first of all we consider some wind speed, and after that, consideration of that wind speed, what we need to do is that we need to assign some coefficients. We need to multiply this wind speed with some coefficients, and accordingly for various shapes the country course gives us some various coefficients for the calculation of the final wind load values. So I shall take only 10 minutes of your time in explaining all of this, because otherwise if I went into depth of explaining each and everything, then the length of this video shall be more than 1 hour. So consider it as just as a short briefing. So first of all we refer to the basic wind speed. So after calculating that basic wind speed, that is VB, that we can see it with the help of the map that I shall show you in the next pages. After that, to calculate the VZ, that is design wind speed, we multiply the basic wind speed, that is VB, into K1 into K2 into K3 into K4. This K4 factor has been introduced in 2015 only. So 10 years back when I was designing, I never used this K4 factor, but after 2015 I started following this K4 factor. So here we can see that the K1 value is probability factor, that is risk coefficient, K2 is terrain roughness and height factor, K3 is topography factor, and K4 is cyclonic importance factor of cyclonic region. Now the terrain categories are also classified, that is terrain category 1, 2 and 3. 1 we can refer it as flat plain without trees or open sea coast. Category 2 we can refer it as, for example, the built up outskirts of towns, suburbs, open parkland, or open airfields. Terrain category 3 we can consider, let us suppose we are talking about this internal industrial areas and industrial towns, or this residential area that you might be living in. So all those areas are classified in category 3, where there are various number of obstructions to the smooth flow of the wind. So according to category 1, 2 and 3, the code further guides us. This is the basic wind speed map that we are talking about. Let us suppose if we want to see the wind speed for Warangal. So Warangal is lying in blue region here, so it might be in 39 or 44. Let us say if we are talking about this Kanpur region here, so for Kanpur it is green color. So green color means that the wind speed is 47 meters per second. So this is the K1 factor, that when we are talking about the general buildings and structures, the K1 factor for 50 meters per second wind speed is also 1, and 55 is also 1. For temporary shed structure that are used during the construction operation, for example formwork and false work, so for those the K1 factor is lesser, that is for example for this 50 meters per second zone area it is only 0.7. so this you need to understand that when we are talking about designing the formwork or false work for the construction purposes, then we don't need to take the full wind speed. Why? Because the life of that formwork or scaffolding is very less. That is it may be maximum 28 days or 30 days, not more than that. And in that short duration there is a very less probability that maximum wind speed may occur. So buildings that represent a low degree of hazard to life, or for example wooded areas or farm buildings, so here we can see that the coefficient is somewhat higher. And important buildings such as hospitals, communication buildings, towers, the wind speed factor is 1.08 for this 50 meters per second. So these are all just simple calculation for K2. This it varies as per the height also. So here we can see that for terrain category 2, and for example let us if we're talking about the height 15 meters, this coefficient is 1.05. So all these for terrain category 4, where there are various obstructions to the flow of the wind, here you can see that this K2 value is very less. Topography factor is a factor that I had used only, and that you also used to me, that you also need to use only when we are talking about the structures in the mountainous regions. That is, due to the profile of the mountains, the wind speed may increase or decrease. So to consider that profile, we need to consider topography factor K3, and this is the paragraph for K4, that is importance factor for cyclonic region. So when we are building a hospital in a cyclonic region, we need to take K4 value as 1.3. So after the calculation of Vz, that is Vb into K1 into K2 into K3 into K4, we calculate the design wind pressure Pz, that is 0.6 into Vz square. After that, design wind pressure Pd. This is the value that has also introduced in the 2015 only. That is Pd is equal to Pz, that is this value, into Kd into Ka into Kc. Kd is nothing but wind directionality factor, Ka is area averaging factor, and Kc is combination factor, and this Kd into Ka into Kc shall not be less than 0.7. So Kd is wind directionality factor. For circular or near circular form, this factor may be taken as 1, but otherwise it is 0.9. Ka is also depending upon the area, that is when the area is tributary area less than 10 meter square, Ka is 1, but when it is greater than 100 meter square, it is Ka is 0.8. So now we are clear that how we can calculate the Kd into Ka into Kc. Kc is a factor that is given much after all this concept here. So for that you can refer 4.5.3.3.13. And coming back to the main concept, that how we can calculate the wind force. So to calculate the wind force, you need to refer to this formula here, that is Cpe minus Cpi into A into Pd. So Cp is external pressure coefficient, Cpi is internal pressure coefficient, into A, that is the area, surface area of the structural element, into Pd, that is design wind pressure in Newton per meter square. So whatever value that you should calculate here, it shall be in the units of Newton per meter square. So this is the value that guides us about the openings and the Cpi internal pressure coefficients. So building or structures with medium openings between about 5 to 20%, we need to take internal pressure coefficient at Cpi of 0.5 and minus 0.5. So for larger opening larger than 20% of wall area, it shall be plus 0.7 and minus 0.7. So for external pressure coefficient, it is saying that you need to refer to the tables only. So these are the tables, main tables that we do need to refer. So this table number 8 is for the calculation of the wind load on the walls of this structure. So let us say in this structure there is side sheeting also with some openings. So to consider that side sheeting area with the openings, what we need to do is that we do need to take the coefficient from this table here. So as per the building H by W ratio and L by W ratio, we can refer to what exactly is the CPE. So these are the coefficient for the pitched roofs, and these are the coefficient for the walls of the rectangular clad buildings. So similarly for the monoslope also, in our case the roof slope is like this. So in some case you may need to refer to this monoslope arrangement also. So they had also given the coefficient for the double sloped roof also. So for various type of sloping arrangement, they had given various types of coefficients and various types of tables. So this is the arrangement for the curved roof. That is for curved roof, H by L, they had given the various coefficients here. So around cylindrical structures also, they had drawn this diagram here. So this is an example for water tank arrangement here. So this is just a simple typical portal that we can see here, but this is for the upper roof surface of cylindrical structure standing on the ground. So this structure is basically a cylindrical structure, not the one that we are modeling in the stat. So you can see this is the typical arrangement for a stadium arrangement. So for stadium, they had given various coefficients here. So this we refer when we are designing the high-rise buildings, or when we are talking about, let us say, any story RCC building. So coming back to our Excel file here, so we had already calculated dead loads and live load. Now we shall consider how we can calculate the wind load also. So we can consider the basic wind speed as 50 meter per second. K1 we can refer it as 1. K2 we can refer it as so if you consider 10 category 2, our height is in the range of only this 10.6 meters. So here we can increase it to, let us suppose, 1.01 only, not more than that. So we can take this value as 1.01. K3 factor, we can consider this area as only in the plain region, that we can consider K3 as 1. K for Assignemnt factor also we can consider it as 1. So Vz we can refer it as 50.5 meter per second, and Pz we can calculate as 0.6 into Vz square, that is 1.53 kN per meter square. After that we can also refer to the Kd, Ka and Kc also. So Kd and Ka we can take this value as 0.9. Ka we can refer it as 0.8. So K is a value that depends upon the area that we are talking about. So conservatively what we can do here is that we can refer it as Ka value also as 0.9 only. Otherwise what we can do is that you can calculate the area that we are talking about, and accordingly we can calculate the area averaging factor. And linear interpolation is also acceptable. That is when, let us suppose we are talking about this 17.5 meter square area. So in that case we can consider the K as 0.95. So similarly we can refer the combination factor Kc also. So Kc we can take it as 0.9. so this Kd and Kc comes out to be 0.729. so design wind pressure PD is 1.53 into this 0.729. so design wind pressure PD comes out to be 1.115 kN per meter square. After the pressure coefficient we can calculate the area of the openings also. So in our case we not talking about any architectural drawings, so we can consider the enclosed condition of the building as enclosed only, not partially enclosed or open. So we can consider CPI as plus minus 0.2. H upon W is nothing but this eave height, that is 8.8 divided by 36. So it comes out to be, H by W value comes out to be approximately 0.244, and L by W, that is this 8.4 divided by 36. So L by W comes out to be 1.07. so in our case L by W is between 1 and 1.5. so what now we need to refer is that we need to refer this tables here. So table 4 and 5 as per 875 part 3, or we can refer to table 8 or 9 as per this NBC 2016. so NBC and IS both things are same only. So in our case what we need to do see is that this is the case that we are talking about here. So here we can see that L by W is lying between 1 and 1.5. In our case L by W value is 1.07. So coefficient of for wall we can refer to table 4 here, and for wind angle 0. So for wind angle 0, and we can see that the coefficient for wall left and right is plus 0.7 and minus 0.2, that is both of these values. And for 90 degree it is minus 0.5 and minus 0.5. so we are talking about this A and B only, we're not talking about the C and D. So after that what we can see here is that for the gable and also that is coefficient for wall for gable 1 and 2, here we can see that for 0 degree it is saying that minus 0.5 and minus 0.5 and plus 0.7 and minus 0.2, that we had copied here. After that for coefficient for roof we need to refer the table this next table here, that is table 5 or table 9 as per the NBC 2016, that is this table here. So here we can see that for this the input variable here is H by W. So our h by w is in the range of 0.244. So it is less than 0.5. So for roof angle of 10 degree, here we can see that minus 1.2, minus 0.4, minus 0.8 and minus 0.6. So minus 1.2, minus 0.4 and minus 0.8 and minus 0.6. So I am zooming in for your clarity here. So this is the wind angle 10 degree. Here we had already seen that our h by w is 0.244, that is less than 0.5. So for 10 degree we are referring minus 1.2, minus 0.4 and minus 0.8 and minus 0.6. So that we had copied here. So now we are done with entering the coefficients here. Now we need to calculate the main values, that is CPE minus CPI into A into PD. That is the wind force that we are talking about. So this value we shall calculate with the help of these diagrams here. So now it shall be better if you revise this whole concept again, read the wind load again, and go through this lecture again. So cause I want to start now with entering all these values in the next lectures. So do please read the NBC 2016 code or Indian Standard Design Code for the wind load values, so that in the next lecture when I am explaining all of these values here, you can understand or grasp easily. So in this lecture we shall talk about the big elephant, that is we should learn how we can calculate and how we can assign the wind load for a pre-engineered building shed. So here first of all I want to explain this Excel file here. So up to this point I had already explained that how we can calculate the coefficients and how we can derive our coefficients from this table 4 and 5 as per the Indian standards. And if you want to see the references for KD, KA and KC, that also are attached in this Excel file here. So here as it is written that when we are talking about the wind load on frame of flat building, for the combined effect of wind load on frame, rotation factor of Kc is equal to 0.9 may be used over the building envelope when roof is subjected to pressure and internal pressure is suction, or vice versa. Now coming back to the diagrams here. So there are 4 diagrams here, that is wind across the ridge with negative CPI, wind across the ridge with plus CPI, wind parallel to ridge with plus CPI, and wind parallel to ridge with minus CPI. And after that there are 4 more diagrams here when we are talking about the wind columns, that is a cable ends sections here. So here we can see that same in this scenario here only, that is wind across the ridge with minus CPI and wind across the ridge with this plus CPI. So here we can see that this is wind parallel to ridge with plus CPI and wind parallel to ridge with minus CPI. So here what we can do is that this is minus here and this is plus here. So what we need to do is that we need to club the result of this diagram here with this diagram here, this with this, and this with this, and this with this. So accordingly we shall assign our loading. And after that, if you see this here, you will see that there are 8 different types of this load cases here. So you must be thinking why there are 8 when we are talking only about this 4 diagrams here. So as I had explained you earlier also, that this dimension and this dimension is not same. So in the diagrams here also, here you will see that let us say when we're talking about this part here, this value is minus 7.14, that is acting away from the structure, and this value is minus 1.43 kN per meter, it is acting again away from the structure. Now this is a scenario when wind is flowing from this side. What if the wind is flowing from this side? So here we can see that this dimension is more and this dimension is less. So in that case, again what we need to do is that we need to reverse the loading, that is 6.43 kN per meter will act from this direction, and suction of 7.1 kN per meter will act on this rafter, and minus 1.43 kN per meter suction will act from this rafter here. So that we shall learn by practical application, but before that I want to explain you how and what exactly are these values here. So this 0.9 that we're talking about here, it is nothing but CPE minus CPI, that is F73 here plus 0.7, and here we are talking about this minus CPI value here. So minus is basically plus, so minus and minus 0.2, so 0.7 plus 0.2, that is why the 0.9 value is written here, and this 0.9 value needs to be multiplied with A into PD. So in our case we are talking about the kilonewton per meter. So what we need to do is that we need to multiply the gable length and we need to multiply the wind pressure here. So if we check the this cell here, so here we can see that this is my 0.9 into 1.15 into the gable spacing, that is the base spacing, that is 6.4. so 6.4 into 1.15 into 0.9, it comes out to be 6.43 kilonewton per meter. So we shall start by the application of this loading in our structure. So first of all we shall apply 6.43 kilonewton per meter UDL. So direction we shall take it as X, and we can select all the vertical columns here. So now we can see that this positive means it is towards the structure element. After that 7.14 and 1.43 suction we shall apply. So we shall add 7.14 minus 7.14 plus 7.14 and 1.43. So we can select all of these members here. So here we can see that it is acting away from the structure. Now there is this one more thing that you should understand. This suction shall act perpendicular to the direction of the rafter. So how we can apply this perpendicular, that I'll also explain in the previous lectures, that we need to take Y local here. So observe the difference here. Here it is you can see that it is in acting against direction of gravity. Now when we select the local Y here we can see that now it is perpendicular to this direction here. So this is the difference of selecting local Y and global Y. So here also we need to select this local Y here. So we can select 1.43 here. Similarly we can select all of these members here. And 1.43 we need to select for these members here. So now this loading and this loading has been applied. This is 0, so we don't really need to apply this loading, but we need to take care of the this gable end also. So for the gable end, what we can do is that in addition to the loading that is acting on these wind columns, what we need to do is that we need to take the 50% of this value here. So we can take it as member load, global direction X, and 3.215, that is 6.43 divided by 2, and considering local Y here we need to enter 3.57, that is 7.14 divided by 2, and 1.43 divided by 2, that is 0.715. So we can take these members here, that is 3.215 and 3.57 for these members here, and 0.715 for these members. So now we are done with wind load minus 0.2. In the only the loading that is missing is this wind load across the ridge with minus CPI, that is WL1. So for minus CPI, we can see that it is acting away from the structure. So we need to apply 3.18, and how this 3.18 value is we can apply. We need to refer this gable end spacing here. So in this base spacing for gable end, right now we are talking this 9.5 meter, but as per the this dimension here, we can see that the maximum this gable end spacing is 9 meter only. So we can take it as 9 meters, and this value here that we are talking about, it is nothing but this coefficient, that is CPM minus CPI into PD into this gable end spacing. So now we are done that. We shall need to apply 3.01 kilonewton per meter away from the structure. So we shall select member load and uniform force global Z. We need to apply 3.01 plus and minus 3.01. and minus 3.01 for these three columns here. So now this wind load from left and my CPI minus 0.2 loading has been applied, and we need to go to the specification also. In the specification, where we need to assign release and end, and we need to assign release of MY and MZ to these wind columns here. We do need to go to tools and redefine incidence, switch incidence of selected beams. Similarly, we need to redefine the incidence of these beams also. Basically what we are doing is that we are not resting this beam on the face of the web of this column. We are just simply passing it over on the top of this column. So that is why we shall assume that only vertical directions shall pass. No moment shall be transferred from this rafter to these wind columns here. So similarly, we can assign releases to these wind columns also. After that, again we can come back to our loading parameters. So all these loadings are now applied. Similarly, we need to take the mirror loading in this load case. And how we can take it? We can just simply add first of all these values here, that is member load, uniform force GX minus 6.43 kilonewton per meter, and for Y we can take it as 7.14, 1.43, GX 3.215 minus 3.215, and Y as 3.57. I'm just simply copying all this loading values that has already been calculated here, and 0.715, global Z 3.01 and minus 3.01. So this 3.01 and minus 3.01, the behavior is exactly same. So we can just simply copy paste the members from the editor file to save our time. After that, this plus 0.715 and 3.215, 3.57. So whatever loading has been applied for 3.57, now we need to apply it at 0.715. So here we can see that 0.715 is now applied on these members here, and here 0.715 was applied on these members here. So similarly for this 3.57, So I hope you can understand what exactly I'm doing here, that I'm just simply I'm just simply reciprocating all the loading arrangement here. So it shall be clear when I shall do the mean loading here. That is 7.14 kN/meter was being applied on this rafter here. Now in this case it shall be applying on this rafter here, but already we had applied 1.43 kN/meter on these rafters here. To save my time, what I am doing is that I am just simply copying all the members here and then pasting this to 7.14 here. So 7.14 was initially applied on this, but now I am applying it on this member here. Similarly 7.14 was applying on this member here, so I shall copy it to 1.43 here. So this arrangement is just mirror of this arrangement here. Now 6.43 kN/meter, we need to select this vertical members here. And as per this, it is acting towards the structure. So that is what we are doing here, that is we are applying wind load towards the structure, and 50% of it shall act on these members here. So now we are done with wind load from right to left with CPI minus 0.2. Similarly, we need to apply wind load with plus 0.2 and from left direction. So what we need to do is that we need to take the value here with plus CPI and wind across the ridge. So here we can see that positive means acting towards the structure and negative means acting away from the structure. So this is again a somewhat complicated case. So what we can do is that we can add UDL of 3.57 kN/meter along global X direction. So select member load, global X and 3.57. Similarly, what we need to do is that we need to add more member loadings, but before that what we can do is that we can just simply assign this 3.56 kN/meter to the vertical members here and side by side to save our time, and we can add minus 3.57 and global direction is X. So initially we had applied 6.43 kN/meter to all of these members here, so we can just apply 3.57 kN/meter and here so copy all of these members here and paste all of these members here. So whatever member we have applied here, we can just simply copy the name of these members to save our time. After that, this 3.57 kN/meter is done. 9.995 and 4.28 away from the structure. So member load, local Y, 9.995 and 4.28. So 9.995 we shall copy all of these members here. So here we can see that we can copy the name of these members, and similarly 4.28 so now this loading has been applied, and we shall also need to apply the away loading of 2.86 kN/meter. So we can add member load and 2.86, select global direction as global X. So we need to select the name of these members. So here we can see that it is acting away from the structure. So now this loading has been applied, but we also need to apply the loading on the gable ends members also. So we need to take the 50% of this loading, but before that I also want to apply this 9.995 and 4.28 for wind load along right to left, so that there shall be lesser confusion between you and me. So we can add local Y, 9.995 and 4.28. So we can copy the name of these 4.28 members to 9.995, and for 9.995 to 4.28. so this is just a mirror of what we are doing. And after that we also need to apply 2.86 kilonewton per meter. So we can add member load global X as minus 2.86. so it is acting away as what we need to do is that we need to copy the name of these columns here. So now the loading has been applied, but we also need to apply the 50% loading on the gable end sections also. So that also we can do. So now we also need to apply the 50% loading on the gable ends. So for that, what we need to do is that we need to add here and member load global X, and we need to add here as 1.875. And for here we need to select these members here. Similarly, what we need to do is that for this value here, that is 2.86, we need to enter 1.43 kilonewton per meter. Global X, select these two gable end columns and assign to selected beams and yes. So after that, what we need to do is that we need to assign this uplifting pressure on the gable ends. So this value is 9.995 and 4.28. So for 9.995, conservatively we can take 10 divided by 2, that is 5 kilonewton per meter, and 2.14 kilonewton per meter. So member load 5 kilonewton per meter global Y and 2.14. So here we can select these members here and apply 5 kilonewton per meter suction pressure and 2.14 suction pressure on these members. So now we are done with this WLL plus 0.2. We are now pending with similarly applying all of these 50% load cases for this WLR plus 0.2 also. So what we need to do is that for 3.57 conservatively we can take 1.8 kilonewton per meter. So member load and minus 1.8, global direction is X, Y we can take it as again 5 and 2.14, and for global X we can take it as minus 1.43. So for this 2.86 we can select both of these members here. And for this 3.57 we can apply 1.8 on both of these members here. For this 9.995 we can apply this 5 kilonewton per meter UDL on these portals here. Similarly for 2.14 on these portals. So now we are done with this load combination also, but we are pending with the loading on the gable ends also. That is the loading that we had applied here. So we do need to refer this wind across the ridge with plus CPI. So here we can see that the suction pressure is 7.03, that is which is acting away from the structure. So we can add member load, global direction is Z, and plus 7.03 and minus 7.03. So plus 7.03 we can select these wind columns here, and minus 7.03 we can select these three wind columns here. Similarly for this load case also. So now we are done with the wind load along all of these for these four cases. After that we need to consider the perpendicular wind load and CPI as minus 0.2. So what we need to do is that we need to refer this particular diagram here. So here we can see that the CPI is plus 0. Here it is saying that we are now right now talking about the plus CPI, and here we can see that we are right now talking about the minus CPI. So in this case, this is basically the WL4 that we are talking about. So here we can see that there are 4 wind pressure that all of them are acting away from the structure, that is 2.14, 4.28, 2.86 and 2.14. So we can go to this add member load, and 2.14 is the wind load along global X direction, minus 2.14 and plus 2.14. And uplifting pressure is 4.28 and 2.86. So here we can see that this is minus 2.14. So we shall select all of these columns here. And for plus 2.14, we shall select all of these columns here. And after that, for 4.28, we shall select all of these rafters here. And for 2.86, we should select these rafters here. And for the wind column that we are talking about, this is wind parallel to ridge. Here we can see that for the wind columns here, so in this value what we are doing is that we are considering minus CPI, but in this value we are saying that WL3 is with plus CPI. So we can just simply change the name of these. So we can name it as WL4 and we can name it as WL3. So here basically when we are talking, we are right now talking about the minus CPI values. So minus is basically plus here, and this is minus here. So in our case we need to refer this value here, that is 9.04, which is acting towards the structure. So as this is a positive value, so it shall act towards the structure, and in our case we shall add member load in global Z direction 9.04 and minus 9.04. So we shall select all of these members here. So all of these values are acting towards the structure, and after that when we are talking about this these values here, so we do need to take the 50% values for the gable end also. So we can add member load global X minus 1.07 and plus 1.07, 2.14 along the global Y, so local Y, and 1.43. So when we're talking about minus 2.14, so we shall talk about minus 1.07, and when we're talking about plus 2.14, we are talking about plus 1.07. Similarly for this 4.28, we shall apply 2.14 on these rafters here, and when we are talking about 2.86, we shall apply 1.43 kN per meter UDL on these rafters here. So now we are done with this load case also, but we need to apply the reverse for in this load case also. So we shall copy all of these values here. So member load GX minus 2.14 plus 2.14, Y 4.28, 2.86, GZ 9.04 and minus 9.04, minus 1.07, plus 1.07 along global X, and Y as 2.14 and 1.43. So what we need to do in this case is that both of these loadings are acting away from the structure, so we can just simply copy paste this value in the member's name here. As both of these values are acting away from the structure, so it's like both of these values are same. So after that, instead of this 4.28 and 2.86, whatever member we are applying 2.86 kN per meter, we shall apply in 4.28 in the next load case. And similarly for this 4.28, we shall apply it to 2.86. And for 9.04, it shall be same. And for minus 1.07, it again shall be same. And for 2.14 and 1.43, whatever loading is applied on 1.43, it shall apply on 2.14 here, and whatever loading is being applied on this 2.14, it shall apply here with 1.43. So now the things are clear that here it is 1.43, here it is 2.86, here it is 2.14, here it is 4.28 and 9.04 and minus 9.04. So this may be a little boring exercise here, but this is the thing, this is the way things are done when we are applying the, or when we are designing the wind load structure, wind load for a PEB structure. So this is quite a lengthy lecture, I must say here, that we are undergoing right now, but you need to take care of your focus here, because it might be distracting in the beginning, but eventually when you shall practice again and again on various types of structures, then you shall have a control over or grip over this wind engineering calculations. Now the last case that is still pending is this case here that we are talking about, that is wind parallel to ridge with plus CPI here. So wind parallel to ridge with plus CPI, the value all of these values are minus, that is all of these values are acting away from the structure. There are four values here, 5 and 7.14 and 5.71. so we shall take here add member load, and here we shall take -5 along global x and +5 along global x, and similarly 7.14 and 5.71. so we shall take y local 7.14 and 5.71. so as per this diagram here, we can see that this -5 is acting away from the structure. So you can take all of these columns here, and for this again it is +5, and after that for the 7.14 you can see here that it is plus CPI, that is for on the left rafter here. So for that, what we can check here is that we can just go to this value here, all of these members here, we can select all of these members and just copy paste for 7.14, and for these members the loading is 5.71. so now the things are much more rationalized here, and in this case we are just left with the gable end arrangement here. So here we can see that the loading is acting away from the structure and the value is 4.02. so what we can do here is that we can just add member load, global direction is z, plus 4.02 and minus 4.02. so plus 4.02 is acting for these members here, and minus 4.02 is acting for these members here. And after that this 50% loading for the gable end arrangement that we do need to apply. So we can go to this member load arrangement, global x minus 2.5 plus 2.5, 3.57 local direction is y. Here for 5.72 we can take it as 2.86 conservatively. So for this we can apply minus 2.5 loading, and for these members we can apply plus 2.5 loading. So for this 7.14 we need to apply 3.57. And for 2.86 we do need to apply loading on these members here. So now the loading has been applied correctly. Similarly we can apply loading for this last, that is WLP plus 0.2 and minus Z. It shall be just mirror arrangement of all of the loading that has been applied here. So we can just copy paste all of these loadings here. We can go to the member load arrangement and just copy paste all the loading that has already been calculated in the previous load case. So minus 5 plus 5, y as 7.14 5.71, global direction Z 4.02 and minus 4.02, GX as minus 2.5 and plus 2.5, Y as 3.57 and 2.86. So now what we need to do is that this loading and this loading is same, because both of the members are loading is acting away from the structure. So we can just simply copy paste the name of the members here. Here for 7.14 it shall act on 5.71. so all of the members on which the loading acting was 7.14, we shall put it on 5.71. so after that 4.02, we can just simply copy paste the arrangement, copy paste the member's name, because this is a symmetrical arrangement that we are talking about. And minus 2.5 is for these members here, so we can also copy the name of these members here, because it is again symmetrical arrangement. And for 3.57 and 2.86, so whatever loading is acting on 2.86, it shall act on 3.57, and whatever loading is acting on 3.57, it shall act on 2.86. so now all the loadings are applied, that is all the 7 type of wind loading has been applied in our structure. So in the next lecture we shall learn how we can input the design parameters in the start for the design of the PEB shades. So in the previous lecture we have learned how we can assign the wind loading and how we can calculate the seismic loading, wind loading parameters, how we can define the load combinations. Now we shall come to the main part, that how we can enter the analysis. So we'll just go to the analysis option here and then left click on add here to instruct the start to perform the analysis, and after that we do need to go to design and left click on steel option here. So here we can select IS 800 2007 and WST. so here we need to go to the define parameters here. So you shall see various types of parameters that can be entered in the start software here. So here we go, first of all need to go ahead with this general beam option here. So after that, tensile strength and FYLD, here we can select it as 345 grade. Usually PEB structures are made in high strength steel so that we can have more economy, and we can enter LY and LZ also. So to calculate the LZ, first of all we do need to know the various parameters here. So here we can see that LZ for this arrangement here, this column here is 8.8 meters, and so after that what we need to do is that we can enter CAN, that is general beam option for all the main rafters and for all the main columns. After that FILD 345000, we can again assign these to the members that we are talking about. After that we can go to define parameters. We were here, that is at FYLD. After that we again need to enter the LZ parameter also. So LY and LX and LZ, These three are the most confusing parameters for the new structural engineers. So you need to understand some concepts here. First of all, let me mark all the dimensions that we shall see. So here we can see that whenever whenever in modeling we introduce a node at some point, we do need to tell the start software that this node is just a node but a member along, let us suppose this is a single member from this point to this point. So let us suppose if we want to enter Lx and Ly and Lz for this type of structure, so what we need to do is that first of all select all the main rafters and main columns. So Lz for this column shall be 8.8, but Ly for this column shall be 1.5. Now you must be thinking why Ly can be taken as 1.5 meter, because basically when we are designing or when we are dealing with the PEB sheds, we do break the member or we do support the top and bottom flange of the member with the help of purlins at every 1.5 meter interval. So as if you remember in Excel file also we had entered the purlin spacing as 1.5 meter. So we are supporting the columns and we are supporting the rafters with the help of girts and purlins at every 1.5 meter spacing. So what we need to do here is that we need to enter Lz here as 36 meters approximately for this whole rafter here. Left click on after current and add, and for this column we need to enter Lz as 8.8 meter. Let me explain you again in the 3D format here. So here we can see that this is the major axis that I am talking about, and perpendicular to this, that is along this direction, that is along z direction, it is the minor axis, and along the minor axis, that is Ly, we shall provide girts, that is side purlins, and with the help of each and every girt we shall support the top flange also, and we shall support the bottom flange at each and every 1.5 meter interval. So that is why Lz for this column is 8.8 meter, but Ly and torsional constant, that is Lx, both can be taken as 1.5 meter. So we can go to define parameters and we can enter Ly as 1.5 meter and Lx again as 1.5 meter. After that main we can enter this 350 here, and we can select it as design shall be done as per the welded section. So for Lz 8.8 we need to select all the columns here. So all these columns must be assigned Lz of 8.8, and all the middle rafters shall be assigned Lz of 36. That is, this whole arrangement from this point to this point is unsupported along its major axis, and this whole length is approximately z meter. But this this beam from this point to this point, Lz shall be 9.045. and for this it shall be 9.6, for this it shall be 8.6, and for this again it shall be 9.045. So we can left click on define parameters. After current Lz we can enter 9.045, 9.55, 8.56. So what we need to do is that we need to select these members here, and for 9.045 we need to select these members here, and for 9.55 we need to select these members here. So this is just simple math or simple or basic understanding that we do need to tell the start that even if we are introducing a node here, it doesn't mean that this member finishes at this point. we need to tell him that this length of this member along its major axis, that is, if the member sags like this, like in the direction in which I am drawing this shape here, it shall be 9.045. STP2 shall be this whole arrangement here. Main 350 shall be for the bracing. So what we can do is that we can select all of these bracings here, go to view selected objects only, and we'll come back to design and select main as 350 here. And after that, this L, Y and LX, what we can do is that we can select all the members here, because all of the members shall be supported at each and every 1.5 meter interval. So now all the design commands has been assigned. So some of you must be thinking that why we are not applying DJ1 and DJ2. So I shall suggest that I had already explained DJ1, DJ2 in the other lectures also. That is how you can check the deflection with the help of DJ1, DJ2 and DFF. So I personally don't use DJ1 and DJ2. Instead, I check the deflections manually. And if I feel like the deflection is going excessive, then I do increase the sizes manually only. So after that, we can go to the commands, check code and take off. So steel takeoff, we can take these members here, and for this main 350 again we can add the command takeoff, and for check code we can select all the members here. So as I had discussed with you earlier also, that I want check these tie beams here that are only serving the purpose of just simply tying all of these members along the minor direction only. So now everything is done. Properties have been assigned. All the members have been assigned the property. Specifications have been assigned. Support has been assigned, that is all the joints are pinned. Load combinations and load envelope is also defined. Material has been designed, that is steel. Design commands has been entered. So let us check the structure. So we can go to the output file here. So it is showing that some of the members are slender and cannot be checked for the moment forces. So here we can see that member number 1, it is saying that it is slender. Again member number 4. So this member, it is not checking in the design here. It is again not checking in the design. So basically this member here, that is member number 8, we do need to increase the size of this member. See, basically the thing is that here you can see that it is showing the fx, my and mz value. It is also showing the ratios here, but it is just feeling like this. So it is saying that the member is slender. So what we can do in this case is that we can increase the 250, 16, 308. To 50, 16, 350 and 8. Let us again check the behavior. So here we can see that now the warnings have been reduced. Still maybe some members are failing. So here it is saying that elastic Reference load case must be used instead of the load combinations. So this warning I had also explained in the previous lecture, that what basically is the significance of this warning is that it is requesting us to go for the second order elastic analysis. So that also we can go ahead, that is also not a big issue. Or what we can do is that we can just increase the size of that particular member. So coming back to the main concept, that how we can check that whether our structure is safe or not. So we can left click on this member here. So here we can see that it is going up to the 88% utilization. Axial forces coming out approximately 103 kilonewton, and bending moment along for load case 15. That is for this particular load case here, it is coming out approximately 769 kilonewton meter. Similarly for this this part here we can see that this is the negative bending moment, but it is showing in the positive manner. We can go ahead with MZ and click dead plus live. Just select this portal here. So here we can see that this is 769 kilonewton meter. We can also go to the post processing mode. We can go to the results, view value, beam results, bending, maximum, and annotate. So here we can see that this value is 769.281. This is the same value that is being highlighted here, that is 769.281, and here this is 292.8. This is the same value that has been highlighted here. So it is going up to 98% utilization, it is going up to 88% utilization. Same is the case here, it is going up to 99% utilization and 92% utilization. So here we can see it is going up to 95 and 99%. So it is just on the edge of the margin that all of the members are passing here, but it is suggested that we can nominally or marginally increase the size so that we shall be in the comfortable range. See, this is a comfortable range, that is either the utilization issue is in the range of 88 to 95 mm. That is a comfortable range, but this is also comfortable, that is 94%, but this is a very like marginally passed member here. So this is the typical arrangement of the bending moment diagram that you must have studied in the college also when we used to design the theoretical portals. And in the case of various loading, here we can see that this is the loading bending moment diagram under the case of the seismic forces, that is seismic along Z. This is the BMD in the case of dead load, live load, and wind load. So under the wind load, you can see that the uplifting was occurring, so that is why this type of bending moment diagram is happening here. So this is the diagram for dead load plus live load. So various types of bending moment diagram can be seen here. So similarly, we can also check the shear force diagram. This is the axial force and this is the shear force that we are talking about. So if you want to see the shear force, we can left click on shear bending and we can select the load case here. So here we can see that the shear force is coming out approximately 87.5 kilonewton, and this is the shear force diagram. This is a torsional diagram, bending moment along minor direction, which is obviously negligible, and this is a diagram for beam stresses, and this is a diagram for deflection. So we can go to the post processing and we can go to displacement and summary. Here we can see that at some point it is going down by 180 mm. So if you want to see what exactly is the ratio of this, that 180 mm, so what we can do is that 36,000 divided by 200, it is approximately 180 mm. So if we are comfortable with allowing the deflection of this dead load of L by 200, that is 180 mm, then the size is okay. Otherwise what we can do is that we can increase the size of these members here. But what if as a simple rule, if we don't want to click each and every member, check the utilization, we can go to the select by specification in all failed beams. So it is saying that no beam is failing for the this particular arrangement here. And if you want to see the bracing ratio also, it is saying that it is approximately 47% utilization ratio, and Fx is coming out approximately 5.5 kilonewton. So there is comfortable ratio in all of the members here. Here we can see it is also going up to 95% utilization. So all of the earthquake forces are traveling from along this direction here. So here we can see that load case number 38, it is for the earthquake only. So we can also check the design here. So it is showing us the utilization of 42% only. So we can decrease the size of this member. So I hope things are now clear to you, that how you can design the PEB sheds. But just as a practice, what we can do is that we can increase the size of this arrangement here. So we can go to the general property, and instead of 0.766, what we can do is that we can increase the thickness of the flange, and similarly we can increase the size of this. And for fifth, what we can do is that we can increase from 350 to 300 to 350 mm, so that everything is comfortably passed in the next analysis, in the next iteration of analysis. So let us rerun the analysis. So now this is at 94% utilization, 90% utilization, 84% utilization, and 80% utilization. So now all the members are getting comfortably passed. We can go to the stat output here, and we can go to the steel takeoff option. So here we can see that the weight of the rafters and the bracing is coming out approximately 440 kilonewton. It is in the range of 45 metric ton. So the weight of the rafters and the weight of the culpollen is coming out approximately 45 metric ton, that is 45,000 kg, and all the members are passed. So I hope the things are now clear to you, that how you can design a pre-engineered building shed as per the Indian standard. So in the next lecture series, I'm getting this request from past 1 year or so, I think, that how we can design the truss portals. That is, what if the person says that he does not want to construct this in the form of I sections? What if he wants a simple truss in the form of this profile? So in the next lecture we shall learn how we can model a truss profile with this type of arrangement, with the help of obviously the same loading, so that we can save some time, and we can discuss more about the technical aspects of what we can or how we can economically design the portal PEB trusses, so that we can reduce the role of the bending moment diagrams, and we can increase the role of the axial forces in the structure.